So PCA is a way of identifying patterns in data and expressing the data in such a way as to highlight their similarities and differences. So basically, we apply PCA to transform our data set in such a way that the similarities or the patterns that exist in this data set are more easy to find, more easy to detect, more easy to learn by our algorithms. So in data of high dimension, where a graphical representation is not available, PCA is very useful to reduce the dimension, and this will allow us to do a better analysis of the data. If we can reduce the dimensions to be in dimension 2 or even dimension 3, then we can also plot these points and observe if there is some structure in the data set. Okay. But in general, one of the main applications of PCA is to reduce the dimension, so the computation is easier, and the analysis is also easier. A second application is to reduce the dimension because it is a pre-processing step towards the application of a supervised learning algorithm. So this would be another important application of PCA, to reduce the dimension, not only for analysis, but because you are going to use that data set in a supervised learning problem, like for classification or regression. And the third main application of PCA is data compression. So you can compress the data by reducing the number of dimensions without losing much information. And a very clear example here is for image compression. So, which are the steps for PCA? So in the first step, you get the data, you subtract the mean from each of the points in your data set. If the scales of your features are different, then you need to normalize them, as we saw previously. Then you need to calculate the covariance matrix in the same way you calculated the covariance matrix in Gaussian discriminant analysis, for example. You just compute the covariance matrix. Then you calculate the eigenvectors and the corresponding eigenvalues of this covariance matrix. This can be done using any programming language nowadays. It's just a command that you need to give the matrix, and you will be given as a result the eigenvector and the corresponding eigenvalues. Remember that if you are working with a covariance matrix of dimension n, you will get n eigenvectors and the corresponding n eigenvalues. Then you need to choose the components or the eigenvectors and form a feature vector, a new feature vector. So what you do is you check which of the, or you rank all the vectors based on the values. These eigenvalues are simply numbers, are scalars, so you are interested in those values that are the largest ones. So for example, if you generate 10 eigenvectors and you say you want to keep the five main components, the 5 vectors with largest eigenvalues, then you just rank all the eigenvalues and select the ones that are the largest ones. And this is what we're saying here: choose the components. Once you have found the components, you need to form a feature vector. And with feature vector, we will see this a bit later. You simply need to project the points into this component. So you will have your original dataset transform into the new subspace that will be created by your vectors, created by your eigenvectors. And that's all you need to do. You just compute or project your points to derive your new data set. So in general, once the eigenvectors are found from the covariant matrix, the next step is to order them by eigenvalue from the highest to the lowest. This will give you the components, the main components, in order of significance. And if you like, you can decide to ignore the components of lesser significance. You will lose some information, but if the eigenvalues are small, you don't actually lose much information, and you will be reducing the dimension of your data set. So in this final step in PCA, what you do is you derive your new data set by projecting all your points to your new subspace. So once you have chosen the components, the main eigenvectors that you want to keep, you simply take the transpose of the vector and you multiply it on the left of the original data set transposed. This will give you the original data transformed into the new subspace, the new vectors. So mathematically what you do is, suppose that your vector, your example I is this vector here, x, and here we are assuming that the dimension of the vectors is k. All you need to do is to multiply to the left, or on the left, by the vector that you want to use to transform the data set. And by computing this product, you will get another vector, and this vector will be already in the new dimension, in the new reduced dimension. So there is a very interesting application, and it was a very popular one when this work was published some years ago, and it is called Eigenfaces. The idea here is to recognize faces, and this method is based on PCA. You need to compute eigenvectors, and since the eigenvectors represent faces, they decided to name it Eigenfaces. So what they did was to take first a set of faces like this in grayscale, and each of these faces was considered a vector in some dimension defined by the size of the image. Okay, and they computed the mean vector of that data set, and that mean vector will look like this, which is like the average of the faces. They subtracted this mean from each of the original faces, so now the faces were centered around 0, the vector 0, and then they computed the covariance matrix and computed the eigenvectors. They selected the top 7 eigenvectors, so the eigenvectors were the top 7 largest eigenvalues, and they plotted each of the eigenvectors in a matrix form, and they look like faces, and these are the eigenfaces. In this case we are looking at 7, the most important 7 eigenfaces or eigenvectors. And what they did was to transform all the original faces into the new subspace defined or created by these 7 vectors. Okay. By projecting, they did it just by projecting the original faces onto each of these vectors. So what you get is a representation of each of the original faces in a new subspace. And here is an example. This is the original image, and this is the image, the same image but projected onto the new 7-dimensional space created by the eigenfaces. And as you can see, they keep a lot of the information of the patterns of the pixels from the original image. So mainly what they are doing is saying we have these 7 components, and we can reconstruct each of the faces in our dataset by summing some amount of the first eigenface plus some amount of the second eigenface plus some amount of the third eigenface, and so on. So they take a bit of each of these faces to reconstruct each of the original faces. And this is very very powerful concept, because they managed to use these eigenfaces to create a face recognizer. So in face recognition, you have a set of faces in your dataset, and you get a new face or a face as an input, and you need to verify if the input face is similar to one of the faces that you have in your dataset. If you can do that, and you find that this face is similar to one of your faces in your dataset, at that moment you have recognized that person. Okay. So what I did is to acquire an initial set of faces, which is the training set. They calculated the eigenfaces for this training set, and they kept only the m eigenfaces with the largest eigenvalues. With this, they were defining a new subspace they call the face space. If you increase the number of persons in your dataset, then you need to recompute and recalculate the eigenfaces. Okay. Then once you have computed the eigenfaces, you need to calculate the corresponding, what they say, distribution in n-dimensional weight space for each known individual by projecting their face images onto the face space. So you take an image and you project the image onto each of the eigenvectors, each of these eigenfaces. Each time you project the image, one image onto one eigenface, remember that these projections are just dot products, you will get a number, a scalar, as a result of this projection. So if you have 7 eigenfaces, after projecting an image onto each of these 7 eigenfaces, you will have 7 numbers, 7 scalars. Okay, and this is what they call the weights. Okay, so this vector in dimension 7 will be the representation of the original image. Now, once you have done this and you want to apply this algorithm, this program, what you do is you calculate a set of weights based on the input image and the m eigenfaces by projecting the input image onto each of the eigenfaces. This is what you want to recognize a new face. So you take a new face or a new image, and you want to check if you have this person in your dataset. So you compute the weights from this input image. Then you determine if the image is a face at all by checking to see if the image is sufficiently close to face space. So you can define this by comparing the distance, for example the Euclidean distance of this image with respect to the eigenfaces. If it is a face, then you need to classify the weight pattern as either a known person or as an unknown person. So remember that each of the faces, suppose that you have 100 faces in your dataset. Once you have projected all these 100 faces onto the face space, the new subspace, and suppose that you have 7 eigenfaces, then each of these 100 faces will be now vectors of size 7. Okay, when you get this input image, you compute this vector, its vector in dimension 7, and then what you need to do is to check, to compute the distance of this new image to each of your 100 images that are vectors in dimension 7. And you can apply, for example, the Euclidean distance. So you can select which of the 100 images in your dataset, which one of these is the closest one to your input image. And then you need to define somehow a threshold, saying if this image is at least almost this far from the shortest or the closest image, then I will consider that these two persons are the same person. Okay, and you will need to find this threshold to make the final classification in known or unknown person. Optionally, if you get new faces in your dataset and you want to recognize, of course you want to update the eigenfaces, or just by because people changes with time, you can keep updating your dataset with new taken images, so your eigenfaces are updated, so your program keeps working with the new faces. And another optional step is if you see a face, an unknown face several times, you can also incorporate it into your dataset. Okay, so you would classify, maybe you want to include this person as a known person, or maybe as a known person, but maybe it is not allowed to into your system for security, for example, for security applications. So the main steps are, as we saw, the computation of the eigenfaces, selecting the best ones, the ones with the largest eigenvalues, and then once your data is transformed or sent into this new subspace, then we are simply working with vectors in some small dimensional space, and there you can apply just Euclidean distance, or you can even apply k-means or whatever you want to do to process these images. In the case of recognition, what you want to do is to see to be able to compute very fast the distance between each of the images in your dataset and the input image that you want to classify it. So this is all about PCA that we're going to study here. Thank you, You can check the articles if you are interested in applying or learning more about eigenfaces. You can Google this. This is the main paper. They published some other papers related to this one. As you can see, it is from 1991. And well, I hope this is useful. Thank you guys, and talk to you later. Bye.